error fine tuning. Okay, whatever. Yeah, I always spell it like that. So like, I don't even know what's the correct way. Is it like a space? Is it like 2 words? Whatever. Yeah. Okay, let's see if it works. Is it
like add to dictionary? That's the only solution.
Yeah. Let's add it to the dictionary. Yes. There we go.
Can anyone tell if this is streaming? Okay, I see the bot thing join, so I think we're good. Okay, awesome. You want to take it away, Daniel?
Okay, cool. The slideshow. Yes. Okay, well, hello everyone. Well, thanks for inviting me. So yes, I'm the algorithms person behind Unsloth. And so like Unsloth makes QLoRA and QLoRA fine tuning 2 times faster with 80% less memory use. And we support Llama, Mistral, and Gemma. Great work on Llama 3. Yes, everyone loves Llama 3. So like, yes, very good. Yeah. So we launched December 2023. And we try to make like fine tuning very simple and very easy for everyone. And the goal is to make it more accessible to everyone in the entire world. We essentially use Google Colab's free GPUs to host our notebooks, and so everyone likes to use those notebooks. So we support like supervised fine tuning, DPO, everything that's like very popular, like ORPO and stuff like that. And we try to support as many models as possible. There's a lot of feature requests, so I can't handle everything. So we try to like prioritize which one to support. Yeah, we're also going to be doing like Lava and like other like different multimodal type models in the future. Give us a star, and yeah, if you want to use Unsloth, there's like free Colab notebooks in our page, GitHub page. So in terms of benchmarking, so we did like a Hugging Face like mini collaboration with them. So we copy like Hugging Face's like calling mechanisms, but we kind of like streamlined it a bit. So like instead of importing the tokenizer or the model, we just shove it into one system call. And you can like we essentially like you can use .getPeft model, which is like to inject LoRA small little weights to train into the model, and we try to like make it as simple as possible for people to use. And yeah, so like that's kind of the calling mechanisms for Unsloth. So in terms of like our benchmarking, we benchmark against Flash Attention 2, and also PyTorch is like scale dot product attention for like the older GPUs, and yeah, the VRAM reduction and also the speedups. So they're different across different models because they're the models have different architectures, but they're generally like around 2-ish times faster. Some of them like Tiny Llama even more faster, but like that's for some of the models. Yeah. This is kind of this is actually old already. Like I have not actually tested I haven't actually profiled the new the new Unsloth codes, but like essentially the majority of the time it's all matrix multiplications on the GPUs. So I don't actually have the new one, but it's like approximately it's all matrix multiplications, right? So like matrix multiplication, gems, and many matrix multiplications. So that's kind of the yeah. So you can see like there's not that many like there's no many like we've reduced it as much as possible. All of the other like CPU type stuff, and it's all matrix multiplications. Yeah. So some of our kernels, so we spent a bit of time on writing Triton kernels for Unsloth. I don't know if you can see, but it's a bit blurry. I don't know. But like this is just, for example, like cross entropy, the forward pass. I stripped out all the comments because otherwise it won't fit on the screen. So like this is kind of like just the cross entropy forward. We try to make it as simple as people for people to read. It can get a bit cumbersome if you like it's a very large. It can get very confusing for the cross entropy kernel. So like we just try to make it as readable as possible. Okay, this is a large wall of text, but like before we actually do the kernel, we actually have to do some maths to actually work out exactly how the kernel actually, how do we actually write the Triton kernel. So actually I had to like think, I didn't actually know how to write the softmax, the cross entropy loss. I didn't even know like how to actually calculate it. And so like, there's like some tricks that you can do, like, in the the softmax, you actually have to minus the maximum, and so like why do you have to minus the maximum? I have to like learn that, and it's just to make sure that it doesn't like it doesn't make it like explode on like the big numbers will like take over the entire softmax, and the small numbers will like disappear. So like this is just to like normalize the entire equation to make it like much more stable. And I didn't there's like very interesting tricks that you can do, and the maths is very fascinating. I didn't actually know that when you minus the the maximum, you can actually take it out of the softmax if you lose a log. If you use the log sum x, the log trick, and then you can take the constant out, which is very interesting. This is like the RMS layer norm forward. You could see I commented out some parts, like for example, the upcasting to float 32. I think in Hugging Face, I'm not sure exactly the exact like the data types inside, but this, if you don't actually comment that out, like the .2 Triton float 32, it actually will make the loss not match. So I'm not sure if it's just like a upcasting problem, but I used to upcast it. And if you upcast it, actually the loss actually is lower. The training loss actually decreases lower than if you don't upcast. But I think to match Hugging Face's loss, I commented it out. And so that's kind of the forward kernel for the RMS layer norm. I also didn't know you can actually use there's reciprocal square root. I'm going to assume the compiler probably compiled it out. So you don't have to do 1 divided by the square root. Triton, I did not know that you can use RS square root. So that's a new thing that I learned. For the backward, it's a bit more complicated. I actually spent a long time trying to derive the backward for the RMS layer norm. It's very annoying to do. The derivatives can be extremely complicated. And so like I had to like spend lots of time trying to derive the derivatives. And also I found you have to cast everything to float 32. If you do not do that, your loss will be totally wrong. And so everything is upcasted to the float 32. And after so much work and annoyances, the code is actually not that complicated. It's like, some sums and stuff like that, but it is very annoying to derive the derivatives. I think I wrote it in a blog post somewhere about the derivatives. The rope kernel is actually my favorite. So I was actually trying to find how to actually do the rope kernel, like, nicely. Okay, this code looks a bit ugly because I just shoved everything into like, the head positions and all the strides and stuff like this. So it looks very ugly. You can make it look nicer, but this is essentially the rope kernel. And I don't know if anywhere else is like the most, I would say this is probably the most efficient rope kernel, from my own benchmarking. And I couldn't really find another like example of a, one rope kernel, which doesn't use like that many complicated parts. And the hardest part actually was a derivative for the rope kernel. So how do you actually derive the backprop step for the rope kernel was very annoying as well. And I just noticed that it's just, when you do the rotation, rotate half, which is like in Hugging Face of the, matrix, the derivative is just minus of the sign, which is very interesting. And, it's not, you can like essentially the derivative is just like, changing the sign of the sign. Change the sign of the sign. Okay, So we actually changed the rope kernel. So someone actually contributed an even faster rope kernel. So the purple line is the, PyTorch's like general naive rope kernel. Unsloth's old one was a red one, and someone actually contributed something to make it even faster. And I didn't actually know you can do grouped rope kernels. So like you can actually like group so when you load the sine and the cosine matrices, when you multiply the matrix, we continuously load the sine and cosines like continuously. And so you can actually like, group them into like 4 batches, like, load at the same time, for each row, load it like 4 times. And so like you can reduce the, communication overhead as well. And so like, you can just stay in like cache. And so you don't need to like, keep fetching the sine and cosine matrices. And that made it somewhat faster, which is very helpful. A nice community contribution. It makes the rope kernel like, 10% faster. However, the rope kernel, because we like made everything matrix multiplications, it only made training like, 0.25% faster. But it was still a very fascinating improvement. The SwiGLU kernel in Triton, again, like there's some upcasting problems. So like before, you can see I comment out the upcasting. I noticed that if you do upcast, you can actually reduce training loss even further. So I don't know if this is like a interesting phenomenon, but like if you keep upcasting to float 32, your training loss will actually decrease more. However, to maintain the training loss and make it the same as Hugging Face's loss, I commented out the upcasting. And yeah, so this is just general. It's quite simple to do it like a Triton forward for the SwiGLU kernel. It's very, very simple. Yeah. The backward is very involved, very ugly. And it took a lot of time, again, to calculate the derivative for the backward kernel for SwiGLU. The main issue I found was the upcasting problem again. You have to be very, very, very careful to which one you upcast and downcast. So you can see, like, I tried many things, and you can only upcast the one of the items. If you upcast everything, your training loss actually diverges, and it's actually incorrect. So I actually spent lots of time trying to like exactly match the exact upcasting phenomenon. I'm not sure why, but like this is just trial and error. So yeah, and I spent a lot of time like trying to like exactly derive the derivatives. So there are like comments about how to actually derive the derivatives. I don't know if you guys can see, but like it was very annoying to derive the derivatives for SwiGLU as well. And also like I think that we like put in Unsloth, which like reduces a lot of, so we actually reduce actual flops. Was it actually the ordering of operations? So when you do LoRA, it's like, A times B. So it's like W plus A times B. And when you do the backbroke pass, you have to be very careful to actually how you do the derivatives. If you do not bracket correctly, you're actually going to be doing more flops. And so we found that if you bracket correctly, you can actually reduce actual flops. And this actually makes stuff faster as well. And there is no hit to accuracy because the matrix multiplication is exactly the same, right? It's just the ordering which is different. So we had to also derive all of the derivatives as well, which can be very painful again. But somewhat fun. I think like after we did so many derivatives and stuff like that, it's kind of like second nature. And so I wrote down all the derivatives for each of the LoRA weights, for the down, projection, up, and gate. And if you like derive everything out, you can, if you bracket correctly, so you can see I put the brackets, right? It's on purpose. If you bracket in the correct places, you can actually reduce flops. If you do not bracket correctly, you'll be doing like, extra multiplication for no reason, right? There'll be like wastage of computation. On other stuff that we do, so we don't just make stuff faster. So, through community contributions, for example, like Gemma, we found a few bugs in Gemma's implementation across different architectures, like, Hugging Face's implementation, Facebook's, sorry, not Facebook, Google's own implementation had bugs. So like multiple bugs across different implementations. For example, like, they used like, in the Hugging Face implementation and their own, like, the Gemma PyTorch's implementation. So like Google's own implementation, they used exact SwiGLU, which is like incorrect. You're supposed to be using approximate. And this actually reduced accuracy somewhat. And there were many other issues in Gemma's implementation. And so we tweeted out stuff. Yeah. So for example, like, I didn't know why, but like they had to do like square root 3072. And I didn't know that you actually have to like downcast it to B float 16. If you do not downcast it to B float 16, the float 32 version is actually incorrect. And so your training loss will actually be somewhat wrong. And there's like other like weird bugs which I didn't actually understand. So like these are just random things that we found and we fixed it immediately in Unsloth and we pushed it to we pushed it to all the packages. Yeah, so these are some of the some bugs that we found as well. Also, one of the issues we found was, I think Gemma was the first serious open source model which increased the vocabulary size from 32,000 to like over the maximum CUDA block size, right? The max CUDA block size is 653. Wait, I don't remember. 2 to the power of 16 or something, right? 2 to the power of 16. Yeah, 65536, right? So the max CUDA block size is 65536. And the biggest issue was Gemma had a very large vocabulary size. And so all our kernels kind of broke because we did not support larger than 65336 vocabulary size for the cross-entropy kernel. So we decided we had to do something called chunked cross-entropy kernels. So like we essentially do cross entropy across each, like, divide like each block into 65336. And so like each block will have like, a separate kernel invocation for each one. And again, we had to like rewrite all the derivatives as well. And we had to like, learn how to do like chunked cross entropy kernels, which was fun. Yeah, not really, but yeah. So like, for example, this is the cross entropy. Like, how do we actually do chunking of cross entropy, like the cross entropy kernel? Like, for example, if you have a 256,000 vocabulary size, you divide it into four parts. And in order to do that, you have to use the, chunking, the log trick for like chunking. And you can actually do it's like a chunk sum, and you do each sum you can do separately, and then you do a final log sum exponential at the very bottom. And so like if you do this, the trick is like, log sum x, but the chunked log sum x minus 1 is like, it's the same thing. And so like this, like we essentially had to like do something like this to make Gemma work. And then I guess that was good timing because, Llama 3 also has a very large vocabulary. So like, it wasn't like a wastage of effort. So that was very fun as well. Yeah. Gemma's approximate backward kernel is very, very, very annoying. The GLU for the, the GLU, Facebook, Llama uses the SwiGLU, which is very nice. Unfortunately, Gemma uses like, GLU, which is like very ugly. And the derivative is absolutely horrible. I don't know how long I spent trying to derive the derivative. That was absolutely very painful to derive. And I think the biggest issue was we had to like find ways to try to like not use, Triton's like, the transcendental functions. I'm trying to use like weird functions. So we managed to only use one, tan h, just one through the entire like, derivative for GLU. And so like that was actually very hard. I don't think so. I was trying to find another like, research paper how they derived the derivative. And I don't think so there's any paper which like showed you can just use one tan h in the entire derivative. And the rest is just multiplications, divisions, and like, plus and minuses and stuff like that. So that was fun as well. Oh, is it like, wait, okay, yes. Okay, I didn't actually paste my code for this, but like we so we did test. So we did something new, which is called long context support, like I think like 2 weeks ago. And essentially what we did is you can increase, there's only an overhead of plus 1.9%. So the time, you only need to plus overhead 1.9%. And we offload the gradients to the activations onto the system RAM. And the trick is we offload it into system RAM. And at the same time, we use non-blocking cores. So, when you transfer it into system RAM, it like disappears, right? So like we could do computation at the same time as when you like move it into system RAM. I'm not sure if deep speed does this, but I'm assuming deep speed has like something offloading. But I think we made it like very simple for people to use. And so like, we show that you can actually increase context length by 4 times at no cost, like it's a plus 1.9%, extra time. And so like, you can do like extremely long context, using Unsloth now. So like Llama 70B 4-bit can do 48,000 context. If you use flash attention 2, I think it's like 7,000 context. And so that's the green line is the new Unsloth. If you don't use our long context support, then it's a bit, we still have memory reductions, but like it's less pronounced than if you use like our new long context support. Yes, in terms of PyTorch, congratulations on 2.3. Yes, very fun. I especially loved the Triton kernels in Torch.Compile. What a fantastic feature. Finally, I get to use Triton kernels in Torch.Compile. Very good. It was already in nightly, but like, it's very good. It's like stable. So that's very, very helpful. So yes, very good. Fantastic. And also sort of like, support for semi-structured sparsity. I'm going to assume this came from the Xformers, part, but I'm not sure, but like, that's very good. Also like, Torch.AI, like I'm a fan of this, as well. I haven't actually looked too much into this, but there's a lot of kernels, especially like, LoRA and, some of the kernels already in this package. So I'll be integrating this into Unsloth, very good work. Yeah. And also float 8, I was actually very fascinated about this. There's like experimental float 8 support. And that is a very interesting thing because, the new GPUs all have float 8. And so like we still use float 16. And so I'll be experimenting with this in Unsloth, across the next few weeks. Yeah. And also Torch.Tune. I think someone from Torch.Tune reached out to us, like, can we do a collaboration? Yes, we're more than happy to collaborate. I'm just a bit stuck with bugs and stuff. So like, let me fix all the bugs first of Unsloth, and then we can probably do a collaboration. Yeah. And also like there was a research paper which was released, the physics thing. I don't remember the research paper name, like the physics paper name. That was actually very interesting. They found that the Llama architecture does a little bit worse than the GPT-2 architecture. However, when you like train for longer times, there's like the differences disappear, which is very interesting. The most interesting thing I found from the paper was that they found that it seems like float 8. I'm just going to guess that float 8 might be the final precision. If you do more than float 8, like if you do even lower precision than float 8, you actually lose accuracy. So I don't know, like I was going to paste like, llama.c++, the people were testing llama 3, llama 3 8 billion. And if you do quantization to int4, you actually have like much more performance degradation. So I'm just going to assume that float 8 might be like the final precision, like, lowest precision. I know like NVIDIA did float 4 and float 6 for their new GPUs. I'm going to guess that might actually hurt performance. And if you keep reducing precision even further, this is just conjecture, right? So like, the decimal points won't really matter anymore. So like, I'm going to assume float 8 is like the final low precision that you can go for. Otherwise, if you go further than float 8, you will lose accuracy. And so like, so I'm just gambling that float 8 will be the final, lowest precision for GPUs. Yeah, this is just a conjecture. Oh yes, that's my last slide. I was going to put more slides, but I decided just to stop there. I probably like garbled, like, I said a lot of stuff. So like, but if you guys have any questions, more than happy to answer them. Yes, I did like a knowledge dump. Yeah. Anyways, yeah. Thanks.
Thank you, Daniel. Your enthusiasm is like super infectious. I was curious to ask you, like, you've done a lot of work on like the Google Colab's like T4 GPUs. Like, I'm sort of wondering, like, what have you found like useful thinking about those kinds of GPUs versus like consumer ones that other people care about, like 4090s? Like, do you change how you approach the problem substantially?
Yes, that is a good question. So I think the T4 GPUs, because they use float 16, we have to essentially code two pathways. We try our best to like put it together, like, B float 16 and float 16 into one, package. So we do that. But I found like, because of Tesla T4s, they are still pretty powerful, 65 teraflops, and they're for free by Google. So we found that to be very accessible for people to use. For like, the newer GPUs, the 4090s and especially the 4090s, they especially have float 8 support. And so like, we have to like we do need to add like, float 8 experimental support into like Unsloth. And so that's actually very, very important. I do know Google Colab has L4 GPUs now. So L4 has float 8 support. So I'll be using the L4 ones to like, code up. Yeah, I actually don't have a GPU. That's probably my problem. I use online Colab GPUs. My GPU is very bad. It's like some old GPU. And that's probably why I was focused on optimizations. That's probably the main reason. Because I don't actually have good hardware. Yeah. I don't know if that kind of answers your question, but yeah, something like that.
It does, yeah. Thank you.
Gives new meaning to the term GPU for not even to have a GPU. I had a question about the precision stuff. Like, there were a few examples where you were like upcast here, don't upcast here. Have you built any like numerical tooling or something that help you figure those things out, or is it just ad hoc basically?
That is a good question. I think what I do is like okay, this is unfortunate, but I try it and then I look at the training loss, and if it matches, okay, that's good. If it does not match, there is a problem. And so like that's how I do it. Like, I just try every single it's very annoying, but like I try every single combination and see which one is like, matches the training loss exactly. Unfortunately, it's all brute force work. I don't think so yeah, I don't think so there's any like, systematic way to test it. I'm assuming it's because like, it's neural network training. I'm assuming it's like, NP complete. Like you can't actually like exactly tell, if this one's correct and if this one's not correct. I think it's all trial and error. And so like, yeah, it was very, very painful work. So unfortunately, yeah, I just tried all of the combinations. Yeah. Need to charge. Yes.
I have a. Oh, go ahead, Greg.
I was just gonna call on you.
Oh, I have a follow-up question to Greg's question, which is, did you notice any patterns to this? Because we have a similar problem, which is that we like to drop casts to float 32. Sorry, we like to cast to float 32 and then not like truncate them in our generated kernels because it's faster. But then sometimes like we get killed by this. One very interesting case we had recently was the errors were no longer balancing themselves out on two different sides of the equation, and so running it at high precision was bad. So I'm just curious if you saw any patterns.
I think, for example, like for example, the rope kernel specifically, for example, like Gemma, for example, you have to upcast, which is very interesting. And I think Llama does not have to upcast. So Llama, you can keep the rope kernel in float 16 entirely. But Gemma, you must upcast to float 32. Otherwise, there are problems. And so like, I'm not sure why this, I'm going to assume the precision problems can be like, it's like a case-by-case basis. So like, each module, you can upcast or you don't have, okay, wait, maybe let me rephrase. I think the forward kernels are fine. You can like downcast to like float 16. I think that's actually okay. I think it's just the backward kernels that's the problem. When you do the backward kernels, you must be very careful to which place you upcast and not upcast. And if you don't do that correctly, then you can actually lose, the training losses won't match. So like that's kind of what we found. Like, the forward kernels is not that serious. It's just the backward kernels. I don't know why. I think like the trick that we do is you have to do DPO. So when you do DPO, you can actually find all the bugs. If you do normal fine tuning or like normal training runs, you actually can't find the bugs. And the reason why you do DPO is because when you do DPO, the beta is like very, very small. So you're doing like very small updates. And when you do very, very small updates, so you've essentially reduced the learning rate to like a very small number, you can find all these like bugs. And so that's kind of like what we do. We found that DPO, if you do DPO, you can find all the bugs. And you can like carefully fix this one, fix this one and stuff like that. I don't know if I answered your question, but like that's, yeah. Okay, I don't think so I answered your question, but yeah.
That was really interesting. I have more, but Christian, go ahead.
Oh, I mean, I was just going to ask the usual sort of, have you tried Torch.Compile? Has it been working for you? Have you compared the performance?
Yeah, so I actually tried Torch.Compile at I think like last year, December, something like that. One of the issues that there is a lot of memory use through Torch.Compile, especially when you do fine tuning. I'm not sure if you guys fixed it a bit, but I think it's generally the memory use. Another problem is when you do LoRA, but the good thing is like LoRA is now supported for Torch.AO. I think like the graph breaks can be quite painful. And it can actually make problems come up randomly prop up. I'm assuming you guys have fixed it currently, so that's good. But I think in general, I'm very happy for the Torch.Compile support with Triton kernels. That's very, very good. And so like, I think generally the speedups, if you use Torch.Compile, it will be nearly the same as Unsloth. But I think it's just the memory consumption that's the biggest difference. So we have like memory reductions and speed improvements. So I think the memory consumption is still the differentiating factor. So we provide like an 80% memory reduction than normal Hugging Face. I'm not sure about I haven't actually tried Torch.Compile recently, but I am going to again, and I'll probably report back on any differences. Yeah.
All right, I guess kind of related to that question. I'm kind of curious about your thoughts on to what extent are the optimizations you do today things that you could see a compiler doing fairly easily, versus stuff that you think is hard for a compiler to do. And I guess question number 2 is, are there what are the kind of, from my understanding, Unsloth is very much kind of just you manually handwrite the forwards, you manually handwrite the backwards. you manually write, Triton kernels and so on. And so I guess my question number 2 of that is, are there cases where you find this to be quite painful, that you feel like it should not be this painful?
I think the entire process is quite painful. It's fun. It's fun. It's definitely fun, like writing all the kernels forward and the backwards. It's definitely very fun. But sometimes it can get very annoying. It is true. I do use, the trick, you can use like, Torch.Compile. You can take the Triton code out and you can like inspect exactly what Torch.Compile does. And then you can see the generated kernels. That is very helpful. Not all the time though, like, sometimes it can't, it's also very cryptic sometimes as well. So like you have to like manually see, how did they generate the Triton kernel and stuff like that. Some of the variable names, can be quite, there's like very many variable names in the generated Triton code. I think like, if this can be automated away, this could be very helpful. I think the biggest issue is still the memory consumption problem. So I think the memory consumption problem needs to be, more focused on. And if that can be fixed, that would be very helpful. I think there are some algorithmic problems as well. So like you can use Torch.Compile for most issues. For example, you can do the backward kernel and the forward kernel, if it's like very simple. But there are like some issues that you can't do. For example, like chunked cross entropy loss, that's probably like an algorithmic change. Or like, for example, like the rope kernel is like a total algorithmic change. You have to actually understand the data layout of the rope kernel and like understand, okay, like, the matrix is like, different like blocks and stuff like that. And like, how do we actually do the rope kernel? It's a bit more complicated. I'm going to assume maybe Torch.Compile paper handle some stuff like that, but I think there's like some algorithmic changes. Also, like, the bracketing of them. Yeah.
Like, to be clear, my general view of compilers is that they are fundamentally very dumb. And so I definitely agree that like things that like are algorithmic changes are generally things that are like quite difficult for compilers to do. So I think like the chunk cross entropy loss, I think is like a good one. I guess, taking a more broad view, I think some of the flash attention is like very much out of the scope of a compiler to like generate from scratch. But I think the thing is like there are other APIs you could plausibly, like there are other things a compiler can do, perhaps on top of like, what you're kind of doing by hand. And so I'm kind of curious about like what are the biggest pain points for you today when you're kind of like hand doing these optimizations? Because I think oftentimes, right, like, when you do like a smarts thing, like that only a human can come up with, there's like maybe like one smart thing that the human is doing, and then there's like 9 dumb things that you need to do to actually like, like realize that in practice. And so I'm kind of curious about like what are those kind of like smart things, and like what are the pain points when it comes to like manually doing this by hand. And so like, for example, one thing you mentioned previously is like the manually deriving the backwards pass, although maybe that's actually also a smart thing. So yeah, I'm just curious about like what are the main pain points for you when you're kind of doing things by hand.
I think it's so actually I tried GPT-4 to try to help me derive the matrix differentials. It was an absolute failure. Yeah, GPT-4 does not know how to do matrix differentials. I do know, like, the autograd engine, with PyTorch is very helpful. They can, like, do all of the entire process of the differentiation. I think it's just the backward pass, which is very annoying. So, like, when the forwards pass is actually okay, right? So the forwards pass, you can just read the equation, you can type it up into Triton. You can just use Torch.Compile for that. It's just the backwards pass, which is the most annoying. Like, for example, the SwiGLU kernel, it's probably my micro optimization problems. I was trying to, like, not use any transcendental functions and stuff like that. That's probably like my optimization issue, like, my personality. But like, we try our best, like, we only used one tanh function in the entire backward pass. And that's actually very hard to do. I'm not sure if there's any like research paper which has done that. But I think the most painful part is the backwards kernel. I don't know. I'm not sure. Yeah, go on.
For example, like I have like personally noticed that this is kind of painful. But for me, for example, what I often do is I just look at what like Torch.Compile provides for the backwards pass. Or I mean, not necessarily even the generated Triton code, but like the intermediate like representation, like when it's still like in a graph format. And so it's like, A10 dot cosine or, whatever ops in that graph. So I guess I'm curious, like, to what extent that is like useful.
Yeah, that's helpful.
Not
yes.
useful.
No, that's actually very helpful. So for example, the SwiGLU, like backward, I actually looked through the Triton, generated kernel for that. It was still a mess though. Like I think like it was helpful. It definitely was helpful. It could like make me like, okay, this is kind of how you derive the derivative. Okay, very good.
I think there's like a slightly higher level format that might be interesting. I can send an example after the call.
Oh, okay, yes, that'll be
like,
good. Yeah,
like the generative training is like definitely more annoying because it's like there's a lot of things that get like cogen and things like that. But there's like a high level representation that is operating more still at the like whole tensor operator level. That I think would might be useful.
Okay, yeah, that would be great. Like, okay, yeah, I looked at the generated Triton code, so like I directly look into the generated Triton code and see like what is going on. It definitely, I actually like that. That's actually whoever did that like idea. That's fantastic. Like that's actually very good. And so like generated Triton code is like a fantastic idea. And yeah, I think like if you could do it for the if you could even do it for the algorithmic changes, that'll be very, very good. Like yeah, flash attention, yes, flash attention is definitely algorithmic changes, like the data movement. I think it's like whenever it's focused on data movement, I think it's like when the algorithm changes to focus on data movement, then it's very hard to compile. Right, so like flash attention is more about data movement, right? So like the chunked cross entropy loss is more about data movement. So once it goes into the data movement territory, I think it's probably hard to compile. But once it's like general maths, it's probably okay. Yeah. Sorry, go on.
I actually maybe disagree with that point. Like some things of like data movement very much is kind of at like the core of like a compiler, and like I don't think data movement is that. Like I think for some like flash attention, for example, I think the trickiest parts are like the mathematical rewrites. Number one are things that I don't think like compilers in general are just like not good at this kind of stuff. And then the second thing is like it is true that for a like back-to-back gem, there's like a lot of complexity involved. But in general, like data movement, I mean, like in some sense, like fusion is all about data movement. Like things like tiling are all about data movement, and these are things I think compilers can handle well. But I definitely agree. Like I think the more mathematical part of it is something that compilers are pretty poor at handling on math.
Yeah, so yeah, I agree. Yeah, the mathematical part is a problem. I thought GPT-4 could help, on that. Okay, it seems like, these language models do need a longer time to. It's funny, you're using language models to like, code up language models to make it faster. But anyways, like, I think like, yeah, I was expecting like, maybe you use like a high level language model to like do some of the optimizations. I would not suggest that, but like, yeah, something, yeah, that could be like useful, but like, I don't know, maybe Llama 5 could be helpful. I don't know. But like, yeah, so yeah, the mathematical optimizations are probably one of the harder parts. Yeah, I'm not sure how to solve that though. Yeah, that'll be complicated. Yeah,
I would agree. Yeah.
Chris, you wanna? Oh, sorry.
Yeah, there's just kind of a like smaller question, but you mentioned that writing the backwards can be pretty annoying and challenging. I'm curious, did you use grad check in the process to like derive the formulas for backwards? I have found that to be very helpful.
I have. So what I do is like I just look at the training loss and see exactly if it matches. So I found that actually the reason why I do the training loss is you can actually find subtle bugs throughout the entire training code. And if your training loss like suddenly diverges, you definitely did something wrong. And like I can see like, if you essentially like try every single step, and then if every single step the training loss matches, okay, you're doing something right. I did do like manual grad checks, like, Torch.org close, and like, I try to pass it through, the function, and then like I try to see if the module is like the gradients match up. That generally does work. I think it works for a while. And then because of engineering, like, as an engineer, I kind of can't be bothered anymore. So like, okay, I check this part, and then the next time I change it, like I totally forget to check. And so like I don't actually have automated tests. So like I don't remember to check. And so like that's why I like to like just check the training loss and see if the training loss matches. And if the training loss like diverges or like, is not matching Hugging Face, I definitely did something wrong. And then there'll be like a time, okay, like which part did I do wrong? Is it like this part? Or is it this part? Like, it's a complicated mess. And yeah. So I do like manual gradient checks.
Okay.
Yeah.
Cool.
Mark?
Yeah, so Daniel, like one thing I really like about your work is that you tend to like support new models like really quickly. So it sort of leads me to believe that you have like a good set of tricks like in Triton that you use to sort of, move really fast. So I'm curious if you could share what some of those are, because like, I mean, I think Triton just has like very few documentation and stuff. So curious how you went about this.
So like, I think when a new model comes, the hope is there are like the components are like composable. That's the hope. So like for example, like Llama 3, I guess like we kind of already knew the rumors is going to be the same as Llama 2. Like there were like rumors. So I think it's more like an investigation approach first. Like, what is Llama 3's architecture going to be? Okay, we thought it's going to be this or like this and this and this. So like it's more like an investigative approach. And so we can plan ahead. Okay, is this gonna come in? Like, is this going to be this like new architecture thing? So we like there's like it's not just code parts, it's more like planning ahead. The tricks that we do are like more behind the scenes. So like that's yeah. In terms of like Triton specifically, that's a good question. I'm actually not sure. I think like once a new model architecture comes along, we just like read through the code. It's just me. So I do the algorithms. My brother does the rest of the product and the stuff. But like I read through the code and like see, okay, does this look like I can like use another kernel that we already have and like, copy paste it and then change it? So like it's more like copy pasting from like other components. And so like I think like once you get a knack for doing differentiation, once you get like a knack for doing the backwards pass and the forward pass, it becomes like second nature. So it's more like just practice. So like, yeah, I don't actually know how to answer your question. I don't actually have like a set of like tricks. Probably I do. It's probably in my head, but like I don't know.
I actually think you answered it though. So thank you. Yeah, that's great. Appreciate it.
Okay, yeah.
I have another workflow related question. So you mentioned earlier that you do basically all your testing by just training your models and seeing how they converge. Now here at PyTorch land, we very rarely test our changes this way. So I'm just very curious what this workflow looks like. Like how long does it take for you to get results? How many runs are you running in parallel at any given point in time?
You can just test 3 steps. So LoRA, I noticed, because LoRA, like specifically for LoRA, when you do LoRA, because A and B, the matrices, you initialize them, right? So like the B matrix is initialized to be all zeros. And A is like, uniform, like random normal numbers, right? So like when you do the backwards pass, when you do actually the gradients, they alternate. It's like an alternating minimization. So like, because the B is all zeros, when you do the second step, A will become all zeros. And so once you're at the second step, the gradients are fine. But then once you go to the third step, step 3, the gradients must match up together. Like if they don't match up to the original Hugging Face code, you're definitely doing something wrong. So you only need to run your, specifically for LoRA. Okay, this is just for LoRA. If you do LoRA, you only need to test 3 steps. And then you can see, I don't need to like run this for the 2 hours or something. I just need to run it for like 2 minutes. And then I can already inspect if it's right or wrong. And if the losses match up on the third step, you just run for like 60 steps. You see if step 60, the loss like looks the same. The loss curve looks the same. If there's any like random bumps and something, then there's something wrong. If you do like full training, I'm assuming you can I'm assuming it's still similar, right? So like if you do like actual pre-training, you just need to inspect a few steps, right? You don't need to inspect the whole run, right? A few steps you can already see if there's some errors, right? All we need to look at is the fractions, right? If the fractions don't match up, they're like, the loss is like, 13.8112, right? It needs to be at least 13.8116, right? It needs to be somewhat similar. And if you see something there's like some difference in like the fractional components, there is definitely something wrong. So you don't need to run this forever, just a few steps. Yeah.
Yeah, I had a couple of questions. One, is all the code that you write in Triton, are you hand writing anything? And then 2, the part where you talked about like finding mistakes in the implementations, what do you attribute being able to find that? Like, is it sitting down doing the math with pencil and paper? Yeah, those are my 2 questions.
Yeah, so okay, interestingly, the first question, so like I used to work in a video, so you would expect me to write CUDA code and do C++ and CUDA code and stuff like that. I decided not to do that. And the main reason is, if you just do CUDA code, you're not going to be able to like support future hardware agnostic type devices, right? We want to support AMD, we want to support Intel GPUs, we want to support like NVIDIA. And so like the whole goal was like, we don't want to do any CUDA at all and just do Triton. So like everything is Triton throughout the entire package. So that's the first question. In terms of the second question, I don't know, like we just read through the code, like, when a new implementation comes, like, Grok or like, Gemma, or like, for example, like Phi, right? So we found another bug a few days ago. Microsoft's Phi, the sliding window is supposed to be 2048, not 2047. So like they quickly, silently changed it. So they fixed it up. I do not know why they deleted the repo and re-uploaded the wrong error with 2047. So I need to like ask Hugging Face why they did that again. So they put the wrong one up again. So like, I think it's just like, we look through the entire code, we just read it. And I think because like, we did so many models, I think it's like second nature, like, okay, there's like an error here. And it's like just looking at the code. But then sometimes that doesn't work. So we also use like Torch.close, we check the gradients if they match up. There's like many tricks that you can use. You inject like, Torch.close throughout the entire code, right? It needs to all close everything, right? So like every single step you put this in, and sometimes it won't work, sometimes it won't match up. Yeah, it's lots of manual work. Yeah, I wish there was like some sort of like automatic checkout. I don't know. I'll probably make something like that. Yeah, I don't know. Like, yeah.
New York.
Yeah, in that vein of automatic checkers, I think I would echo what Dries was saying. For the gradients, at least, we have a grad check tool in Torch for the grad that you can use to make sure that your code is mathematically correct. So that, FP64 math of your formula is going to be good. If your question is with low precision d-type being good enough or not, yeah, you have to do convergence checks, basically. In terms of doing like, is every op one after the other correct? We have some fun tools to do these kind of things, and we do these kind of things as well that use a concept of mode. You can ping me on Slack and I can give you some examples, but we have these kind of things that basically hook on every single function that run and make sure at every step, does it match the other version, basically. And then you can do fancy stuff like, if the model runs for long, you can also say, oh, here there is a, 1e-7 difference between the two, which is okay in FP32. But you can also correct that error so that, you don't compound the error and you recorrect every time and make sure that you never diverge by more than, something that is FP32 precise, something like that. So that it can be a good way as well to run the full model and make sure that nothing at every step diverges too much. Obviously, it won't help, if you were looking for that divergence to get the convergence behavior for the whole model, but yeah, we can definitely help you with these kind of tools that exist.
Yes, okay, that's fantastic. Like, as you can see, I'm doing this all manually. So I inject code. Okay, unfortunately, yes, okay, I'm a manual type person. Like, I like to like inject every single line, Torch all close, and it's true. Like, the main issue is like if there's one small little issue, the loss will like diverge over time and it accumulates. And I think that's why like if you run it for 60 steps, you can actually kind of see, like the loss is not that diverging, and then it diverges and diverges and diverges, after 60 steps. And so like, once it's around 60 steps, I think, like, after testing. So like, yes, okay, I will probably check. Okay, I'll probably ping you then. Yes, okay. I think I've heard of grad check, but like I never use it because like, I just do manual. I just like run the through and then I check I check the .grad each one separately. That's what I do. So like, yeah. The reason why I do this is because I can actually take the gradients and like see, why is it different? Like, I can actually plot out, okay, like, is it the entire gradient that's the problem? Or is it like, just some small, like the diagonal or something like that, or like something like that?
You can allow our error reporting in grad check. Our error reporting in grad check reproduces the whole Jacobian matrix. So you can actually have the full visualization, not of a single .grad, but of the full Jacobian matrix and where it doesn't match. So it's even easier to read than manually looking at the .grad and where they don't match.
Oh, I'd be like wasting my time then. I should have done that. Okay, okay, I will do this now. Oh, okay. Whoopsies. Okay. Oh well.
Well,
Yes.
no, that's
Well,
on
thanks for
us.
the
I guess
suggestion.
that's Jeffrey. That's a good thing for us. We need to advertise that better.
Yes, yes. Okay, yes. Okay, I think I've heard of this before, but I've never. Okay, yes, I can see. It uses all clothes inside. Oh, okay.
Yeah.
Interesting. Is there like a decorator for this? Like, or like, is it just a? Oh, it's just.
Oh,
the
this
entire
one
function
is you
plus
give it any
clothes.
function and sample inputs, and it will check that.
Oh, okay. Could it be like a decorator? Okay, I'm assuming there's like a. Interesting. Okay, I will try this out. Okay. Yes. Well, thanks for the suggestion.
Any other questions?
I mean, you might find that grad check, like a different way of calling or using grad check works better in your workflow. That would be great info for us too.
Yes. Okay. Okay. I'll try it out, and then I will report back to see exactly. Yes, I will. Okay. Yes, there's lots of like different.
Yeah, we have a
I feel like
collection
wasting-
of extension points that you can play with. That's for sure. Yeah.
I don't think it's wasted
Whoopsies!
time.
They're like
having done it
wasting my
that-
time. Yes, sir.
No. I wouldn't
sorry,
say
sorry, go
so.
on.
I mean, the feel you're getting for it by doing it manually is not going to be lost. It'll be better to use grad check now, having built that up, than if you had just started with grad check. That's my guess.
Yes, definitely. It'll probably save me lots of time. It's like I think like checking like gradients all the time, like it can get very annoying and very, very, very painful. Yes, can get very, very painful. So like if it can like automate away like my stuff, that'll be like much more helpful. Yes, I will be using this. Thanks a lot. Yeah.
Have you ever used like SymPy or another symbolic matrix differentiation tool?
I've used it like a long time ago. And maybe I should use it again. I've used it a long time ago. And the reason why I gave up on it was like I couldn't do the differentials like, nicely. You can get the differentiation of the matrix like differentials, but it's like a jumbled mess. Like, it's so large and like, cumbersome to like play around with. But that actually is a good point. I would try that I didn't actually know Desmos. Like Desmos is like an online, graphing tool. You can actually do derivatives in there. Like I didn't actually know that. Like, you can just type any function that you like and you do the derivative and it can like numerically derive the derivative, which is like very interesting. And so like, okay, I will investigate SymPy more. I kind of gave up on SymPy. I would use it again.
It's what I used way back in the day for deriving the autograd formulas.
Oh yes, okay, very cool. Yeah, okay, I will, yes. As you can see, I'm very manual work. So everything is like manual labor. Why did I not know this? Okay. Yes, I'll do SymPy again, yes.
Cool. Any other questions from folks?
I guess I'll ask another question. So like previously you mentioned like memory is like the main the main obstacle, and yeah, this makes sense. I'm curious, like where do these memory optimizations mainly come from? Is it like primarily about like saving less activations? Is it primarily about making sure things don't get materialized that are like too big at various points? I'm curious like where that mainly comes from.
Yeah, for example, like our latest like long context thing, that's like more like, don't actually do the activations, like save it to disk, like save it to the RAM and like carefully like don't actually materialize it in like CUDA memory. That's like one of the optimizations. But like in terms of like the Triton, it's more like try your best not to like do copies of data. Like when you do the gradients, can you like do it as much in place as possible? That's probably the most important thing. And you have to be very careful. Yeah. Sorry.
How you think about the memory problem? Is it like you think about there's like weights, gradients, optimizers? Yeah, I'm just curious, like how you generally think about optimizing memory.
I don't know.
But look at the profile and see where it is.
No, I think it's So I think I tried using the memory profile now. It keeps breaking. I do not know why. So Okay, maybe that's one problem. So like I try to use profile, like, Torch profile is actually very useful for like the timing. But if you run it for too long, I do not know why it does not work. So you actually get out of memory. So like I don't know if that's a bug or is that like if you run, like if you do more steps, like if you do 60 steps, Torch profile actually breaks. I'm not sure why. And it takes like very long to run. I like after 3 hours, I let it run and it still hasn't finished.
I'm guessing that's just a limitation of like you're trying to dump a profile file that's like tens of gigabytes or something like that, and that's why it's breaking.
Okay.
I guess speaking of like the memory, like have you seen like the memory snapshot thing?
I think I gave up on after the Torch profile broke. I think I gave up on trying to use Torch profile. So like that's probably I will probably use it again. If it's fixed.
The memory snapshot is not part of Torch profile. It's a slightly different thing. You can look on Google PyTorch memory snapshots. Yeah.
Is this a new thing again?
Yep.
I do not.
Yeah, it's
like past half year or past year, maybe something like that.
Past year, and I mean like doing that. Oh yes, okay. I saw some people using this, like the yes, someone actually posted on Unsloth Discord about like a profile, like suddenly like the memory spiked, and then like it didn't really spike. Yes, I remember this. I think the problem. I don't know if this works in Colab. Does this work in Colab? Like I think that's probably the problem. Unfortunately, I don't have a GPU. That's probably the reason. I just use Colab. So if this works in Colab, I'll be using this.
This should dump a pickle file, and then you just need to drop that pickle file in pytorch.org/memoryviz. So as long as you can download that pickle from Colab and drop that on our website, you will get that visualization. Yeah.
Oh, okay, great. Okay. Whoops! I need to get a GPU then. Anyways, yeah. I just use Colab, like the Colab GPUs to program. Yeah.
Yeah, well, you can probably save it to Drive and then just get it in that way from Colab. I mean.
Okay. Yeah. Okay. Interesting. Yeah.
Wait, so
but
I guess I just out of curiosity, like, why do you develop on Colab? Is it just purely like a resources thing, or do you enjoy the experience?
I think it's because like our users, for Unsloth users, I think like 50% of them just use Colab. So like my view was like you have to develop on the platform that they're using. So like if you use your own GPUs, like yes, you can do that. But like I feel like Colab, it's just like it's next to the user, like it's directly what the user uses. So like that's why like we develop on Colab.
So you're saying even if you had your own GPUs, you would not develop on Colab?
No, I don't think so. I'll use Colab. Yeah.
I see. Interesting.
Yeah, but it's good. Like they have the L4 GPUs finally. They said they're going to add H100s. So like the Google people said like they're going to add H100s. So like that'll be interesting. So you can use H100s in like Colab. Yeah, and it's also the cheapest. So like the reason why we use Colab is it's the cheapest. Like Tesla T4s are like so cheap, like 30 cents or something per hour or something. Yeah.
Awesome. So we are out of time. Thank you so much, Daniel, for coming and explaining Unsloth, and hopefully we passed back some useful information as well. Yeah, thanks so much.
Yeah, thanks everyone. Yeah.
See you.
Okay. Yes. Bye-bye. Thanks a lot.